Thank you very much. Let me thank the organizers for inviting me and giving me the opportunity to give a talk. So I'm a THET theorist, and I'm going to talk about THET theoretic results, but I think the flavor of these results and kind of the motivation behind them kind of fits well into this workshop. Okay, so what is the story? So, as I guess all of you know, so in descriptive set theory, we show that like simply definable sets, so for example, Borel sets, they have a very deep and canonical structure theory. And maybe also know is that canonical extensions of ZFZ, so say large cardinal axioms or forcing axioms, they allow us to extend this theory to more complicated sets. And so, I mean, this is not the original result and it's not optimal, but I just want to phrase it this way. So if there's a super compact cardinal, so you don't have to know what it is, but it's just a very large cardinal, then there are no projective well-orderings of the reals. So projective here is definable in second-order number theory. And you can do it with less than a super compact cardinal, and you get more out of this. But let's look at this statement here. So there's so we all know that there are no Borel well-orderings of the reals because there cannot be Lebesgue measurable well-orderings of the reals. And if we have like these nice new axioms, for example, large cardinal axiom, then we can extend this to projective sets and to much more. And often implications of this form are used to measure like the beneficial influence of candidates for new axioms. Because we say, okay, well-ordering of the reals is kind of something pathological and it shouldn't be definable. So these axioms decide the question whether there's a projective well-ordering in the right way. Okay, and now it's kind of natural to ask whether we can also do something similar with larger definable sets. So now look at sets that are kind of subsets of the power set of omega 1 instead of the power set of the natural numbers. And there, it's not hard to see that higher cardinals have like too strong combinatorics to have like a direct analog of the classical theory. And in particular, basically all of the results of the type that I've just shown you, they fail. And now to give you an example, so I said projective sets, and just to have a way to generalize this to higher cardinalities, observe that some set of reals is projective if and only if we can define it in H aleph 1, so that's a collection of all hereditary countable sets, by some formula with some parameters. So it's just definable in this structure. And what we can do now, if we view projective in this way, then we can just replace omega by some higher cardinal. Okay, but now these direct analogs, they often fail or they are independent of ZFZ. So for example, and I guess Sai and Peter Hulli were the first to show this, or to show something that implies this. So if super compact cardinals are consistent with ZFZ, then the theory, it doesn't decide whether there's a well-ordering of the power set of omega 1 that's definable in H aleph 2. So in this collection of sets that have hereditary cardinality at most aleph 1. And the reason for this is you can force the existence of such a well-ordering with a small forcing that preserves the supercompact cardinal. And the other way around, if you add a lot of cone subsets to omega 1, then there's no such well-ordering. Okay. So in general, we cannot just take the classical theory and transfer it to higher cardinals, but we can do something interesting in certain very restricted settings. So let me give you one setting that will not be the topic of the talk, but just to give you an impression of what can happen here. So in this work on very large cardinals, so large cardinals close to the Kuhn inconsistency, would in showed that it's possible to derive a lot of analogs of classical results at very large singular cardinals with completely different proofs than the original results. So, so just one consequence of this theory is if you are at such a very large cardinal, so remember that the Kuhn inconsistency tells you that there's no embedding from v lambda plus 2 into itself, non-trivial embedding. So when you try to get close to it, something very close is having an embedding from L of v lambda plus 1 into itself. So that's very close to the Kuhn inconsistency. And when you have this, then lambda is a strong limit cardinal of countable cofinality. And it turns out that for this model, for this L v lambda plus 1, the structure theory looks very much like the structure theory of L of R on a determinacy. And you can prove a lot of analogs of classical results for this model with completely different proofs. But the structure theory is sort of the same. So in particular, you get the conclusion that in V, no well-ordering of the power set of lambda will be definable here. Okay. So that's one setting where you can do something interesting. I want to talk about another setting where take a different approach. So you look at small cardinals, say omega 1. But what you do now is you look at very simply definable sets. So you drastically reduce the complexity of the formulas and the parameters. And then it turns out that now, like these canonical new axioms, they do something good for these simply definable sets. So let's first fix the notions I want to talk about. So some class X is definable by some formula phi and some parameters if it's just the class of all solutions to the formula. Okay, so this is what I mean when I say definable. And then some formula is a sigma 0 formula if it's contained in the smallest collections of theoretic formulas, so just epsilon and equality as symbols. And the collection contains all atomic formulas, and it's closed under negations, disjunctions, and bounded quantification. And then I get something more complicated by adding an unbounded existential quantifier. So in this talk, I will basically only talk about sigma 1 definability. So you have one unbounded existential quantifier and something that's sigma 0 following that. Okay, so for some uncountable kappa, I will look at subsets of the power set of kappa that are definable by sigma 1 formulas, and the parameters have hereditary cardinality at most kappa. So I don't want to take the set I'm defining as a parameter, so just to stop us from proving trivial things. And I mean, these collections, they have nice properties, and these are given by the fact that we have the sigma 1 recursion theorem. So if we do recursion by using a function that's a sigma 1 function, then the function we get out of it is sigma 1 again. And we have sigma 1 upwards absoluteness. So sigma 1 formulas are upwards absolute between transitive models. And this is something at higher cardinals you will often use, that you take some formula that holds in V, and then you do something like a large cardinal iteration, and you go to some smaller model, and then the formula still holds there by elementarity, and then you use upwards absoluteness to go back to V. So this is something kind of a nice and very useful structural property. And basically, you use these two things in all proofs. But you have to do something more to prove interesting results, because it turns out that if you look at sets definable this way and you allow arbitrary subsets of kappa as a parameter, and kappa is an uncountable cardinal, then you can still do too much coding into the parameters. So you still get that a super compact cardinal does not decide whether there's a well-ordering of the power set of omega 1 that's definable by a sigma 1 formula with parameters of size L of 1. Yeah, so there's still too much coding going on. So you have to restrict yourself even more to get something interesting. But then this can be done. So So now we allow only very small parameters, but we have to kind of allow one big parameter so that sigma1 definability doesn't trivialize. So we pick the simplest parameter of size kappa, namely kappa itself, and then we allow all smaller parameters. And then we can do something interesting. So together with Ralf Schindler and Philipp Schlicht, we proved, I mean, again, we proved this from a much weaker hypothesis. But if you have large cardinals, then no well ordering of the power set of omega 1 is sigma1 definable using parameters omega 1 and things in h omega 1, so real numbers. Yeah, so here you again kind of get these results where large cardinals tell you that pathological sets are not simply definable. And I mean, the real large cardinal assumption we use is measurable above a wooden cardinal, and you cannot do it from a wooden cardinal alone. So this is not a trivial conclusion. Okay, so just to give you a hint of what's going on, so what is behind the theorem is the following characterization of sets of reals definable in this way. So if we have large cardinals in our universe, then a set of real numbers is definable in this way. So by sigma1 formula with real parameters, if and only if it's sigma1,3 boldface. Yeah, so these sets, if we talk about definable sets of reals, then these are just the sigma1,3 sets. And you need large cardinals to get this equivalence here. So it's not a ZFC result. And then, I mean, you kind of directly get the theorem from this, from the second theorem, the first theorem from the second theorem, because so if there was a well ordering of the power set of omega 1 that's definable in this way, then there's a well ordering of the reals that's definable in this way. But this would then be a sigma1,3 well ordering. But large cardinals tell you that these sets are Lebesgue measurable and whatever, so this doesn't exist. Okay, so this is how this result is proven. Okay, so now we can do something similar at higher cardinals that kind of have strong combinatorial properties. For example, we get basically the same conclusion for a when we look at the power set of a supercompact cardinal. So if we have a supercompact cardinal, then no well ordering of its power set is sigma1 definable from the cardinal as a parameter and smaller things as parameters. And there, a better hypothesis is either wooden cardinal below a measurable cardinal or measurable cardinal above a wooden cardinal. Right? But you cannot do it from a measurable alone, so you need more than a measurable cardinal. So these are kind of an example where you can do something like this for regular cardinals, and you can also do something like this for singular cardinals. So together with Sandra Müller, so we proved that if you have a limit of measurable cardinals, then no well ordering of its power set is sigma1 definable from this cardinal and small parameters. So the same conclusion. And I mean, the proofs are they're all different. I mean, they have the same flavor. So for omega 1, you do generic iterations of countable models. For the top theorem, you do real iterations of small models, but with like measures in them. And here you kind of do systems of iterations using these measurables below. Okay, so this is kind of the complexity where there's a nice interaction between like canonical axioms and non-definability of pathological sets. Okay, and there are many other results where it can be shown that some pathological set is not simply definable in this sense if the cardinal has certain strong combinatorial properties. For example, you can prove something like Matthias results on that there are no analytic mad families. So you can prove something similar like this for omega 1 under large cardinals or for large cardinals themselves. Okay, but what I want to do in the rest of the talk is do something kind of the last thing I did when I worked on this topic. And this is joint work with Omer Ben-Neria from Jerusalem. And what we do there is we kind of look at definable closed unbounded sets, so some key combinatorial objects at uncountable regular cardinals, and we look at the definable version of this. And it turns out that these kind of questions are related to like deep combinatorial issues and important questions. So we talk about this. So just a quick reminder for your set theory lecture. So some infinite cardinal kappa, then some subset is closed unbounded if it's unbounded in the cardinal and it contains all of its limit points in the cardinal. And then some subset is stationary if it intersects every closed unbounded set. So think about sets containing a closed unbounded sets as measure 1 sets and stationary sets as things of positive measure. And then so like basic results from the first lecture in set theory show you that the fact that at an uncountable regular cardinal, the collection of all sets that are not stationary, so the non-stationary ideal, so that this collection forms the normal ideal, this kind of captures maybe the key aspect of the combinatorics of uncountable regular cardinals. In contrast, this definition trivializes if the cardinal has countable cofinality. Because if you're at something at countable cofinality, then something is stationary if and only if it's co-bounded, right? Because there are cofinal omega sequences. So in particular, I mean, this is trivia, but there are no bistationary sets. So an important theorem, basic theorem at uncountable regular cardinals is that the club filter is not an ultra filter, so there is a stationary set whose complement is also stationary. I mean, this fails here, right? Because the complement of a co-bounded set cannot be co-bounded. So the theory is just trivial there. Okay, but now we want to look at the definable version of this. And so the cardinal will be kappa, and often kappa will be singular. So this will be interesting at singular cardinals. N will be 1, basically all of the time, and A will be basically just the small sets. Right? So we now say that a set is sigma n A stationary. So we restrict stationarity by just saying it intersects all club subsets, but the club subsets are now definable in this way. So they are like the singleton, they are the unique solution of a sigma n formula with parameters in this class A, and we also always take the cardinal itself as a parameter. And then just boldface means that I take all of the small subsets as parameters for free. And if I don't write A and boldface, then it's really just, so this means sigma n formula using kappa and small sets as parameters. So what I had before. Okay, so now you can look at this notion and you can ask many questions. So in particular, you can ask, okay, so these are obviously all stationary sets are definably stationary. Are there non-stationary sets that are definably stationary? So this is an obvious question. And what about the situation at countable cofinalities where stationary is just trivial, but is there something interesting going on? And also, I mean, stationary sets, so at uncountable regular cardinals, that I mean, non-stationary sets form a normal ideal, so they have a lot of structure theory and lots of nice combinatorial properties. Can you do something similar with these sets at certain cardinals? Okay, so just to give you an example where these notions do not differ, so where stationary is the same as definably stationary. So if you have Martin's maximum, then for boldface sigma 1 stationary, so we look at clubs that are definable by a sigma 1 formula with omega 1 and real numbers as parameters. That's actually the same as being stationary. And the proof is just a result of Woodin. So if we have Martin's maximum, then we have a principle called admissible club guessing. And this means that every closed unbounded subset of omega 1 contains a set of this form. So you have some real, and you just have the ordinals where this is admissible. And this is a club, and for every club you can find a subclub of this form. Okay, but these things, this club here, this is sigma 1 definable from omega 1 at x. Yeah, so if you intersect all definable clubs, then you intersect all of these clubs, then you intersect all clubs. So I mean, yeah. So yeah, the club generated by this. Yeah. Or, okay. Okay. So in this setting, these things are just the same. And I mean, if you have CH, then they are not the same at omega 1. Because you can basically just, they're only, if you have CH, then you have only Aleph 1 many definable clubs. You take the diagonal intersection of them and remove the limit points. This will be definably stationary, but doesn't contain a club. Okay, so now let's use this concept to do something interesting. Let's look at Johnson cardinals. So remember that a cardinal is Johnson if and only if for every function that maps finite subsets to the cardinal itself, there's a proper subset of the same size as the cardinal that's closed under the function. So that's a Johnson function. And one of the big open questions in set theory is, can Aleph omega be Johnson? Or the other way, does ZFZ prove that this is not Johnson? And I think this question motivated PCF theory, for example, or the development of PCF theory. And so how is this connected to this topic? So if the first singular cardinal is Johnson, then we have a lot of sets that are definably stationary but not stationary. So every infinite subset of this thing here will be sigma 1 stationary. Yeah, so these notions differ in, like the classical stationarity, I mean, this is just co-boundedness in this setting. This differs from definably stationary in the most extreme way. I want to say some words how to prove this. So in order to prove this, we do something called the undefinability property, or the sigma 1 undefinability property. And for this, you take two uncountable cardinals, mu and kappa. And the idea is that mu is something small and kappa is something large. And the question is, can you define something in between in a sigma 1 way by using the large cardinal as a parameter and things of small cardinality as a parameter? Yeah, so that's a question. And something has the undefinability property if it's not possible. So for every ordinal in the interval between mu and kappa, this ordinal is not definable by a sigma 1 formula that uses the large cardinal kappa and the small things as parameters. Okay, so this is the undefinability property. And how is it connected to the previous thing? So if two cardinals have this property, so this undefinability, then this singleton mu, so the smaller cardinal, that's a stationary set for the clubs that are defined in a sigma 1 way by taking kappa as a parameter and things below mu as a parameter. And the idea is that, So this thing has to be in all of the clubs that are simply definable, because otherwise you can define kind of the next point above mu from this club in a sigma one way. So from this undefinability property, you get that these ordinals are stationary for parameters below the ordinal or below the cardinal. And then if you have this for many things, so if you have some limit cardinal kappa and you have an unbounded set of uncountable cardinals, where for everything in the set you have the undefinability property with kappa, then this set will be sigma 1 stationary. Okay, and this is how this is connected to Johnsonness, because there you get these sets. Like these are just the Aleph ends. How do you show this? So there's a strengthening of Johnsonness called row bottom, and this is just saying that some cardinal kappa is new row bottom if whenever you have a countable first order language with some predicate symbol and a structure of size kappa, so the larger cardinal, and the predicate gets evaluated as something of size lambda, then this has an elementary substructure still of size kappa, but the predicate now is smaller than this nu. So this is nu row bottom, and so nu row bottom implies Johnson, and the least Johnson cardinal is nu row bottom for some nu. And I mean, if Aleph omega is Johnson, then it's the least Johnson cardinal. So you are row bottom for some Aleph n. Okay, and now, so maybe this is just a technical way to prove this in the end, but from row bottomness, you get some substructure of H kappa plus that contains kappa. I mean, maybe I shouldn't talk about this too much, but you get a nice elementary embedding that sends the cardinal to itself and moves something below. So this is kind of the set-theoretic setting you're in, where you get something strong out of it. And then using this, you can show if omega omega is omega n row bottom for some n, then this has the undefinability property. Yeah, so this is just using this these kinds of embeddings that you get from it. So the corollary is the theorem that if the first singular cardinal is actually Johnson, then this set here is definably stationary. Okay, and I mean, the idea is, so this is really just the first step, maybe in some program, that maybe a possible way to refute this, that you assume this and you get some conclusion about structural behavior of simply definable sets that is just not possible. Yeah, so there's something interesting going on here. I think that you can use this assumption in such a fruitful way. Okay, so the next thing is I want to take just a closer look at this conclusion here and see that it has certain consistency strength. Sorry, I want to do something else. So what you can do, I mean, this doesn't refute Johnsonness, but you can use it, Johnsonness of Aleph omega, but you can use it to show that in certain models of set theory, Aleph omega doesn't have strong partition properties. So what I just said. So what we can do with this is that so in the standard models for forcing axioms, so take a model of GCH where you have a supercompact cardinal, and then do the Baumgartner proof to get PFA, or do something more fancy to get a strong forcing axiom. There we can show that omega omega is not omega 2 row bottom. So there's some line of getting something out of it and restricting the models where Aleph omega has these partition properties. So what we can do is assume that you're in the following setting. So assume that there are no special omega-2 orange entries, so certain combinatorial objects of size omega-2 or size Aleph 2 do not exist, and this is something you get from forcing axioms at Aleph 2. And assume that above omega-2 there are special orange entries. So this is something you get from GCH. And this is exactly the situation you're in when you start in the model of GCH and you do Baumgartner's forcing to get PFA. So then you're in this situation, because when you're in this setup, then you can define omega-2 in a sigma one way from omega-omega without other parameters. So you do not have this undefinability property. Yeah, so you have some ordinal in the middle, basically, that you can define from some large cardinal, larger cardinal. Yeah, so here, this gives you a definition of omega-2, and this shows that the omega-2 undefinability property fails, so you are not omega-2 row bottom. So this is something like, maybe not a big payoff, but something in the direction we want, that we use this definability arguments to say, okay, in these models of set theory, this big open question has a negative answer. Okay, so now let's look at this conclusion that the set of omega n's is sigma 1 stationary. So we get an equiconsistency result for this. So this was the conclusion we got from Janssonist of Aleph omega, so that every definable club in omega omega contains one omega n. Yeah, so this set is sigma 1 stationary, and we can also add ordinals as parameters if we want. So this is equiconsistent to singular cardinal where there's some subset of singular cardinal of countable cofinality where some subset of cardinals is boldface sigma 1 stationary. So we can just take any singular cardinal and look at this type of conclusion. And that's actually equiconsistent to a measurable cardinal. So the conclusion we get for Janssen is not that strong, but it's kind of more interesting to have it kind of as a natural implication. What is interesting is if we do the same thing for uncountable cofinalities, because then this conclusion that there is a singular cardinal, so singular of uncountable cofinality, with now like a weaker property, namely that there's some non-stationary subset that is sigma 1 stationary. So, I mean, if you remember this set of omega n's, this is of course not stationary in the undefinable sense. But if we just have some non-stationary set that it's definably stationary, so this is equiconsistent to having the same thing where we also allow ordinals as parameters. So this is kind of for free, but this is equiconsistent to uncountably many measurables. So for the countable cofinality, we just needed one measurable cardinal. And here, we basically, the result shows that we get as many measurable cardinals as the cofinality of the cardinal. So you need cofinally many measurable cardinals for higher cofinalities. Okay, so this is one interesting thing that happens in the setup. And now the last thing. So we look at disjoint definably stationary sets. And there, already said this, but you remember that there's this classical result of Soloway that says that we can split stationary sets. So in particular, there are bistationary sets. So there are sets where both the set and the complement are stationary. And I already said this. So of course, this doesn't happen at countable cofinalities because stationary means co-bounded. But let's see what happens in the definable context, because this is now kind of just to make it look more interesting. So what we can prove is that there is so this is now a ZFZ statement. So there's a definable cardinal, so something that you can define, so delta, and it's provable in ZFZ that whenever I have some parameter set, so any set of size less than delta, and any singular cardinal, then if I look at clubs that are sigma-1 definable from this collection, subsets now of this cardinal, then there are disjoint stationary sets. Yeah, so if we have just less than delta many parameters, then I can define a definably stationary set whose complement is also stationary, definably stationary. Okay, but now what's the interesting part? So we also have an equiconsistency result. So the following are equiconsistent. So there is some singular cardinal where for every subset of H kappa of the cardinality, this delta, so that I can define in the beginning. So delta doesn't depend on the singular cardinal. It's just one cardinal for every singular cardinal. So I have this singular cardinal where I also find disjoint sigma-1 stationary sets for a parameter set of size delta. So the existence of such a singular cardinal, this is equiconsistent to a measurable cardinal. Yeah, so, and remember, delta is just something I can describe. So, and but I mean by describing something, I mean like omega or omega 1 or the continuum. So the question is, what is delta? I mean, maybe someone has seen this talk with ideas. I mean, this is not for the set series, maybe even more for the set series than in Vienna. No idea? It's a reaping number. So this is some invariant of the continuum. And it was kind of surprising that, so we talk about definability and singular cardinals, and I mean, the proof uses like dot Jensen core model and whatever, and somehow the reaping number pops up here. Okay, let me tell you what it is. So the reaping number, that's the smallest cardinality of a subset of the infinite subsets of the natural numbers, with the property that for every infinite subset, there's something in this family such that either the complement is finite or the intersection is finite. So I kind of either guess the set or the complement modulo a finite error. And then you can prove that this is the cardinal invariant of the continuum, so this exists. This is uncountable, and it has size at most the continuum. And I guess you can prove lots of things about this, like relations to other cardinal invariants. And this is actually kind of the thing that pops up in this proof. So whenever I have a singular cardinal and some parameter set of size less than this reaping number, so now, again, this is any singular cardinal, and like this fixed size, then I find the set that intersects all clubs definable by a sigma-1 formula with this parameter set, and also the complement intersect these sets. So this is kind of the ZFZ result. This is the ZFZ result, right? So below parameter sets of size, below the reaping number, I can always find like definably bistationary sets. And the other way around, the parameter set is this reaping family, basically, plus maybe something extra, right? But if I allow parameter size of sets of size equal to this reaping number, then having something where I have sets that both intersect all clubs sigma-1 definable from this family and also the complement intersects them, then this requires a measurable cardinal in our model. I think this is kind of a nice result because it brings together like three areas that seem kind of unrelated. And actually, when we started proving it, we kind of wanted to figure out what the reaping number for singular cardinals is. And then we realize that it's actually really just the reaping number we are talking about, and it's just not something that depends on the singular cardinal, but it's actually the invariant of the continuum. Okay, and this is all I wanted to talk about. Thanks.